2010, a volcanic eruption took the world by surprise.
We have to be quick and get out as fast as we can.
With an even bigger eruption looming, can experts predict when and where it will happen before it's too late?
Everybody was going down, they need a harness and a helmet.
Yeah, I'm coming!
It is overdue.
To find out, scientists embark on a journey into Iceland's volcano. The rumbling began in March 2010. It was just another eruption in Iceland, the world's most active geological area. At first, the world paid little notice as the lava spluttered and moved into the lower valley. But soon, the volcano caught everyone's attention. And the almost unpronounceable Eyjafjallajökull has a second chapter in store for the world. During the eruption, the ash cloud spread all across Europe, bringing international air traffic to a standstill, with the airline and tourism industry alone losing more than $4 billion.
The situation is, as you can see, it's dark as night. The volcano is right up here, and everything is covered with ash. It's about 10-15 centimeters. Everything's covered.
The eruption of the Eyjafjallajökull volcano changed world opinion. From now on, no one will take Icelandic eruptions lightly. The magma is still on the move deep inside the earth. Will it erupt in the much bigger neighboring Katla volcano, like it often does within a year or so of an Eyjafjallajökull eruption? Historic evidence leaves no room for doubt. An eruption in the Katla volcano will be of catastrophic dimensions. Can scientists learn to predict what's next and understand why some eruptions are more violent than others? Bringing scientists underground could be a first step in understanding what happens inside a volcano. Not far from the 2010 eruption site, another of Iceland's volcanoes offers just that opportunity. The Thrínukijager volcano is the only place on Earth where humans can descend into the volcano's magma chamber. Veteran climbers Bjorn Olafsson and Einar Christian Steffensen are on a mission to uncover this chamber's secrets and pave the way for a future scientific expedition.
On Everest we go up, but here we are going down into the very heart of Mother Earth. So it's a bit different.
Even though this volcano has not erupted in some 3,000 years, descending 150 meters into the magma chamber is a risky undertaking. One small loose rock falling in here could easily kill them.
Okay, how was it? It was a bit too fast in the middle section.
Their task is to map the magma chamber. If they can find the lava tubes that once fed this volcano, this place offers scientists an unprecedented opportunity to understand what caused the Eyjafjallajökull eruption to behave like it did, and perhaps tell them what will happen next.
Leave 10 centimeters of each foot. the primary goal we have is to survey the whole interior of the chamber and measure how big it is, the volume. And our preliminary results, I would estimate about 100,000 cubic meters.
So, and are we all set?
Yep.
Okay, I'm going to move up to Mark and follow
Yep.
All right.
Take care not to look into a red beam. It's a laser. It can damage your eyes. We have created a reference plane and we're starting scanning the southwest face of the inner surface of the crater. We've scanned for about 1 hour and 50 minutes now. It's going to be almost 1,200 points.
Bjorn and Einar's measurements build a 3D model of the known system inside the volcano. The upper part of the magma chamber forms the crater. 2 lava tubes continue into the earth, and most likely they were the conduits feeding the magma flow when the volcano erupted. But a mystery remains. Where did the magma disappear to? Why is this the only volcano that's been left standing and empty? To answer those questions, a full scientific expedition will need to be mounted into the crater. After the 2010 eruption, scientists descend on Iceland's volcanoes from all angles. Volcanologist Haraldur Sigurdsson risks flying up on Eyjafjallajökull to get samples for analysis.
Well, we're just about reaching the crater now, and you can see that it's a lot of steam coming out. The eruption is over, but there's steam coming out because it's groundwater that's boiling here because of the hot rocks that are still in the crater.
Flying over Eyjafjallajökull, he now sees that the neighbouring Katla volcano still looks calm under its heavy glacier. But he knows that Katla erupts in tandem with Eyjafjallajökull within months or a year. Katla is a much bigger volcano, and it poses a considerable threat. But Katla is not alone. There are several large volcanoes in the area, and any one of them can be the next one to erupt.
It may look safe now, but we have to keep in mind that it could start up any time again. So we have to be quick, get in there, do the sampling, and get out as fast as we can.
Now we're coming right up to the rim, and you can see how huge it is. It's beautiful.
This used to be a smooth glacier surface. A tremendous transformation has taken place. It's no longer obvious that there's still a glacier here, 180 meters thick. The ice is covered in a thick layer of ash. There is no way forward. It would be too dangerous to walk any closer. During the eruption, this place was an inferno. Large fragments known as volcanic bombs shot out with the ash. They can be a few centimeters across, or as big as cars. From a distance, they look like black rocks in various shapes. Freezing the picture, we can move in and see that the bombs are actually red-hot projectiles. They hit the ground with tremendous force. Layers of ash quickly bury the bombs.
These are bomb fragments, and in a way they're messages from inside the volcano, because they're telling us about the composition of the magma coming from about 15 miles step.
And the message contains information about the gases inside the rocks. The more gases, the more explosive the eruption has been. The Eyjafjallajökull eruption looked violent enough, but scientists call it a medium eruption. A potential Katla event could be 4 times larger.
Well, the volcano stops erupting because the magma supply from deep down in the earth is cut off. And what happens then is that the magma that is already in the pipe is going to start to cool down and solidify. And then it'll form a volcanic plug. That's why in a situation like this, when the eruption has stopped, we have to be very, very careful and very cautious, because another eruption might break out in a different location, but very nearby. So we don't want to be here much longer. We really have to get out of here.
So there is no way forward into this steaming crater. Thanks to Bjorn and Einar's detailed survey of the Three-Nukiega volcano, a team of volcanologists get a chance to see for themselves. No one has ever attempted to get into the crater this way. The team has come up with an innovative way to lower large numbers of crew and equipment down this narrow opening. They use a winch system, normally used to carry window cleaners outside skyscrapers. With bad weather hitting the site, the situation becomes complicated and dangerous. With the base camp back in order, it's time to ready the film crew and scientists for the journey into the crater.
Firstly, everybody was going down. We need a harness and a helmet. When you get down to the floor, there is a security area from roughly 10 meters of size around the elevator. That's the only place we expect could possibly be any falling rocks.
We're not going to do crazy things for filming. We're just going to make sure we do it the right way and that we're safe all the time. Let's do a good job down there and help each other and just be careful. That's the key thing.
Finally, it's the moment of truth. Time to lower the science team 140 meters down into the volcano chamber.
It's a pretty narrow slit, like a fissure.
Alda Sigurdsson has had close encounters with volcanoes worldwide, but this is a first for him. Freystein Sigmundsson knows the Icelandic volcanoes in detail, but has never had a chance to see one from the inside.
To see these spatter on the walls, like thrown up on the wall, the lava spatter, yeah, just plastered on the wall. But there's really no place on the earth that I know where one can descend like this into an old magma chamber. Normally they would just solidify and there would be no access to the deep inside of the volcano. This is really an absolutely magnificent and unique feature. It is interesting to try to make the link between this observation and our geophysical models of what is inside volcanoes, and I'm afraid that most of our models are too simple. They're very simple. This is more complex. The plumbing system of volcanoes is clearly very complex. Well, I think this may be the clue to the formation of this chamber we are sitting in. What surprises me here is the fact that this is an enormous volume of space that has been drained out. This is something of the order of 100,000 tons of magma that drained out, disappeared. And it's amazing that the walls didn't cave in, that this structure survived. And also, we really need to come to grips with the fact that there was a process by which the magma escaped. Now, we know it didn't go upwards. It doesn't go against gravity. So it went with gravity, probably didn't go downwards very much, so that leaves, it must have gone out to the sides.
There are many layers visible on the chamber wall, indicating this place has been built during several consecutive eruptions. The lower black part is very different, most likely caused by an eruption under a glacier which once covered this area.
It's all breaking up here.
Slide down. And you see there may be some fractures.
But we have to be careful, this is very unstable here.
Should we try to go up here and check if we can see fractures? Yeah, there's a big fracture here.
I see that. There are whole cracks right through.
It's a whole fracture system.
I think this is going to be peeling away.
Yeah.
So this is the way that the cavity gets bigger and bigger.
Plane of failure here.
I think this piece is about ready to calm down. I think we should move out of here a little bit. Watch out.
Yeah.
Although this volcano has been silent for thousands of years, it still sits on a very active volcanic area in Iceland. The earth rumbles and shakes. There is an obvious risk that small earthquakes could dislodge rocks from the ceiling. The bottom of the cave is filled with loose rocks, evidence of continuing activity.
It looks like there might be 3 dikes parallel, or 3 cracks filled with lava there.
Yeah.
2 pretty wide ones, and then 1 very, very fine one. So this is definitely the big fissure.
Wow. This is amazing. And we'll see this. We have the whole dike here. We can touch it. The magma was flowing from here to the surface. The whole lava flow may have been fed by this.
That's right. These are like the veins in the body. You know, these are the veins that the magma flows through the body of Mother Earth.
3,000 years ago, this is how it would have flowed inside this volcano.
But the surprising thing is that magma is very fluid. It's not as fluid as water, but it's some of the magma that moves around is almost like ketchup.
And it is surprising. How can you have something so narrow that feeds a whole eruption? Here we have a proof, almost, that we can take a whole lava field we see on the surface and feed it through a narrow channel like this.
To fully understand how these movements work inside a volcano, the team needs to venture further down. From the initial explorations, they know there are lava tubes extending into the underground, and they hope to find answers there. When this volcano erupted, magma would have come this way into the chamber. Yeah, I'm coming!
It's about half a meter wide here. You can see it very well. So we are in the deeper part of the rift zone, and we can see that the magma came up to the surface. It was really along this crack. And what is truly amazing, that next to the fissure here, we can just move a little bit, and then we can really see the outlet to the surface. The lava went straight up here, and then for some reason it drained back down during the final phase of the eruption. The heat after the magma drained out of here was probably about 1100 degrees Celsius, and it was enough to remelt the magma, so it actually started to float back down again along the walls.
So the surprise continues. It appears that the magma never solidified in the chimney or in the lava tubes the crew walks down. It just disappeared.
the lava needed to find a way, and that was probably related to lengthening of the magma-filled crack that was feeding the system. You lower the pressure, the magma drains out, and it does it probably over a time scale of hours or 1 or 2 days.
This place is important to understand what happened in 2010, because this place shows us that soft rock can easily be eroded by magma. The magma has found a way inside this volcano because there is a lot of soft rock in here. Maybe the same happened prior to the 2010 eruption.
The explorations inside the volcano have added new knowledge that will help paint a picture of what really happened at the Eyjafjallajökull volcano in 2010. But to complete the picture, scientists must look deeper into the Earth, to places no human exploration can reach. The volcanic activities in Iceland will not stop. The country sits on top of a unique volcanic hotspot. Hotspots exist in only a few places on Earth. It's believed that this body of extreme heat acts like a chimney from the core of the Earth, funneling heat and material through the mantle and to more shallow parts of the Earth. Here it forms a large body of magma several hundred degrees hotter than the surrounding mantle. The material transportation makes the center of Iceland thicker, like a bulging lid on this explosive body of heat and magma.
Iceland sort of works like a natural laboratory for all kind of processes that you can observe all over the world. But we have many different kinds of volcanoes in Iceland, and there are many different types of processes you can study all in the same area here.
This Icelandic landscape is boiling hot. But Riki Peterson and Sigrun Reynsdóttir focus their work on what happens deep inside the Earth, and how this relates to the hotspot, seeking the signs of volcanic activity long before the magma reaches the surface.
We can see when we have magma, for instance, coming into a magma chamber, the entire thing will expand. And that's what we measure at the surface, because it's like putting more air into a balloon, and then it will expand, and that's what we see on the surface where we have this expansion of the entire mountain. So the entire mountain is actually moving in some periods up to maybe a centimeter a day. But you can't really feel it when you sit on the surface, because it's distributed over a huge area, so many hundreds of square kilometers.
Basically, we are now trying to measure how this bedrock is moving. This antenna is receiving signal from the satellites, from the GPS satellites, and we can see how this place is moving at the time. And right now, this antenna is actually lifting up. We are registering maybe 6 centimeters of uplift per year because this area is inflating.
So in order to understand what happens 24 kilometers below the surface, the scientists rely on satellites flying high above. The colors on the images indicate various degrees of deformation. By repeating the flyovers, the scientists produce an animated sequence to show what happens over time. Their data shows how Eyjafjallajökull behaved prior to its 2010 eruption. The red field shows how the mountain was pushed up and away from the crater, indicating the magma was moving in the ground to the first eruption site.
We saw the magma moving on the crust, and sometimes it was happening really fast, sometimes it was happening really slow, and then some sites just behave strangely, like station closest to the summit was moving up and down, and then north and south, maybe centimeters a day.
There was a huge phase of warming up for this volcano. We saw earthquakes and deformation on the surface. For 18 years we had magma flowing into the volcano at a deep level, not coming out at the surface, but stopping at a deep level and spreading out there. And those are really, in hindsight, what was the precursors of this eruption.
But to everyone's surprise, the eruption in 2010 didn't start in the volcano crater. The magma suddenly found a weakness in the earth and it moved away from the caldera of the volcano and suddenly appeared as a lava flow between Eyjafjallajökull and Katla. So magma can find surprising ways to the surface. Is this also true for Katla and for a number of Icelandic volcanoes? Where is the magma now? Where inside the Earth is the flow finding a way forward or upwards?
We need to understand how the processes work so that in cases where people live close to volcanoes, for instance, that we can give out a warning and they can get out of the area before it becomes more dangerous.
To understand the mechanism at play in Iceland, we must first go back millions of years in time. It all started at the bottom of the ocean. As the Mid-Atlantic Rift opened 50 to 60 million years ago, magma started to pour out many hundreds of meters below the surface, and the magma spreads over the sea floor in what is now the North Atlantic Ocean. The first volcanoes reached the surface of the ocean 14 million years ago. New land was born 2,700 meters above the sea floor. Unlike other places on Earth, this new landmass got stuck over the continental rift and the underlying hotspot. For millions of years, the outflow of lava continued, slowly ripping the land apart, while at the same time adding new land. And the process continues to this day. This is the fracture where the country is ripped apart. Over thousands and millions of years, the rift widens by a few centimeters a year. Along the rift, old and new volcanoes form a string of craters. On average, there's an eruption every 5 years in Iceland, and the next eruption can happen anywhere along this fracture zone. During the past 500 years, about 1/3 of all lava that's flowed out onto planet Earth has erupted to the surface in Iceland. The biggest eruption in recorded history came from the Katla system in 934 AD. It went on for years, and is the single biggest lava flow recorded on Earth in the past 1100 years. The amount of magma that was produced during this eruption would cover all of Manhattan in a layer 270 meters thick. Every explosive eruption produces ash, and it forms layer upon layer all over Iceland. At the melting margins of the glacier, the layers are again exposed in a succession that resembles the annual rings of a growing tree. The ice becomes nature's databank of volcanic history. Gudrun Larsen is a volcanic historian, and her freezer holds the clues to history, but also the future.
To find out from which volcano, we analyze the volcanic ash, because many of the Icelandic volcanoes have a geochemical fingerprint. So when we know the composition of the ash, we know from which volcano it's coming. This is the ash from day 2 of the eruption in Eyjafjallajökull. And as you see, it's very fine. It looks like dirty talcum powder, so to speak.
This is the ash from Katla's eruption in 1918. The grains are much coarser and fell to Earth closer to the volcano. So each volcano has its own unique type of ash with specific characteristics, ultimately deciding how it will be dispersed. During the 2010 eruption, a brown streak of ash spread out over the North Atlantic from the Eyjafjallajökull volcano. Particles were so fine that they reached high in the atmosphere and rode the winds to all over Europe. So can a 10 times larger eruption from the Katla volcano become an even bigger problem for Europe and the world? Erupting 22 times in the past 1100 years. But studying the ash from Katla's eruptions clearly shows that most of the particles travel north and land in Iceland or in the North Atlantic. northwesterly winds that would bring the ash to Central Europe prevail only 30% of the time. At present, there are no obvious signs of an eruption in the Katla volcano, but people around the world are still concerned.
People are interested to monitor more closely volcanoes that can cause these kinds of problems.
Incredibly sensitive earthquake monitors are dug into the ground around the volcano.
We are adding now 4 stations around the glacier.
The stations now encircle the glacier, and they report any activity inside the crater, which is hidden under 640 meters of glacier ice.
It starts weeks before the eruption itself. You can see increased activity and earthquakes, and we are hoping that we will be able to monitor them more closely than we were able to before.
Kristin Vogfjord at the Icelandic Meteorological Office studies the signals sent from the seismometers around the volcanoes.
You can't just interpret the number of earthquakes just from looking at the map, because some of them, like the ones here on the western flank of Katla, are shallow, indicating that they are related to geothermal activity. Here we can see that about 80% of the events are above 4 kilometers depth. The fact that most of it is shallow, to me, means that the earthquakes are related to geothermal activity.
This land is never quiet. Even if there are no volcanic eruptions, there is always geothermal activity going on. The land is shaking from the rapid movements of boiling water. Water feeds into cavities in the ground and meets volcanic rock that's still hot enough to boil water hundreds of years after eruptions. Geothermal activities are everywhere. In this lake, gases are exhaled from inside the earth. Geothermal activities are not harmless, but they are, of course, on a different scale than most volcanic eruptions. For Bjorn Oddsson, geothermal events are significant because they can melt the large glaciers covering some of the biggest volcanoes in Iceland, including Katla. When glaciers start melting, a considerable pressure is lifted from the volcanoes, like removing a champagne cork, increasing the risk of eruptions.
Katla has been erupting 50 to 80 years interval, so today it is overdue. It's 90 years since it had last eruption.
So to understand what is going on with the Katla volcano right now, Bjorn Oddsson takes to the air. If he sees signs of ice melting, he must find a way of determining if the ice is melting due to geothermal activity or if it's due to volcanic eruptions below the ice. Geothermal activity under the glacier melts the ice. The question is melting increasing, and is it indicating that an eruption could be coming soon? They fly straight over the ice, analyzing as they go. Using the airplane's radar system, combined with GPS readings, they can map out any irregularities on the ice surface. A bowl-like formation on the ice usually means there's melting activity under the glacier.
The deep is from 10 meters to 50 meters, and if you're getting extraordinary increase in activity, we have to look at the volcanic activity and take it seriously, because then we might be seeing a period of volcanic activity increasing.
When the eruption starts, it will take only a few hours to melt away 700 meters of glacier ice, immediately flooding the areas below the mountain, while at the same time making the eruption more explosive as meltwater meets the hot lava.
So these changes have been constant. So really what we're seeing now is not making me worried, it's just adding data to your data bank and then just taking
educated decision of being worried or not.
So will Katla erupt soon, or will one of the other Icelandic volcanoes be first? Did the magma solidify in the Eyjafjallajökull volcano, or has it drained away, possibly to burst forth in the Katla crater? To find out, the team launches an expedition to the still steaming Eyjafjallajökull crater. It looks like solid land, but the trucks are driving on top of a glacier covered in ash.
Last time we were here, a lot more snow. It was easier to travel on the snow. Hopefully we can get up the steep hills.
The way forward is blocked by a magnificent cave of black ice. In spite of the risk, they must cross the ice bridge above the cave.
We're getting real close. Almost there.
Safely on the ground, Rainier, the pilot, has some bad news for the team.
Welcome. Hi.
How's it going?
It's okay. Little bit windy. Wind is coming from the south, then going down into the crater, then it comes up again and makes these rotors, turbulence, vortexes, and that is something that we don't want to be flying into. That would be a one-way mission if you would go down there.
Really?
Yeah. I would rather want to go back home tonight.
We can't wait a little bit and give it a shot in an hour or so?
Yeah, we could. Usually the wind comes down during the day, so it's possible later today.
Yeah.
But as it is now, it's impossible.
And we move over to the lava field.
This is where the eruption started in the spring of 2010. The lava fountains created the hills.
So the mission is to try to find an opening in the lava where we can see into the lava. It's cooling, red glowing hot, to do direct measurements. This one was the first to erupt, and this one is the second. And to see the highest heat is exactly where we have these white spots in the lava is the red one on here.
So even if the place looks benign now, it's still a hot volcano zone.
It will take a couple of years until it cools completely.
The cameraman Johan has geared up for the dangerous task of filming inside the crater.
Good luck.
The wind has come down in the early evening, but that's not the only worry at this stage. Finding a landing spot will be hard enough. As soon as Bjorn steps out of the helicopter, he sinks into the top ash layer. This is not good. The helicopter can easily be sucked into this material and get stuck. Bjorn asks the pilot to fly away while he looks for another landing spot by using the heat camera.
So what you're looking at now in the heat camera is that the blue spots is the snow and the caldera surrounding the crater, and we can see that the red spots here are the tephra sites of the new crater within this cauldron here, and we can follow down north, and the red line is the lava. And you can see this mud here is the last phase of the eruption, probably due to some post-explosive post-explosions, maybe steam explosion. You can see how wet this mud is, and this is causing the lahars down the glacier. And if you're caught in one, you would never survive. So you have to be careful up here. there. You just sink into the mud.
They decide to try flying the helicopter into the crater one last time.
Okay, I think I spotted a place we can try to land.
This is one of the 3 craters that opened up through the glacier during the 2010 eruption. It's filled with meltwater, so landing there is impossible.
It's probably really hot down there, and I can smell the sulfur all the way up here. I hope we don't need masks. We don't have any. So the hottest spot we see here is around 100 degrees. That's on the surface. But even under we get 5 to 800 degrees of Celsius.
Down to the right, there's a small knoll, a possible landing place.
We tried on top of the first eruption site. It might be just as dangerous. But let's try it anyway.
Even though the wind has almost died down, the updraft created by the hot volcano is so strong that the helicopter wobbles in the air.
Slowly. This is unbelievable. Steady.
It's very turbulent, and it's too dangerous. They're forced to abort the mission. Returning to the base, Bjorn and the team soon have success in finding some of what they came looking for. Half a year after the eruption, the rock is still glowing hot right below the surface. Trying to get a temperature measurement, Bjorn quickly finds it's too hot. Only the plastic cover on the cable was burned. The instrument still managed to get a reading.
Yeah, within a half a meter it goes from 30 degrees, which is the temperature outside now, and up to probably around 800 degrees. It's definitely hot down there.
So the magma didn't totally drain out of this area. It just built a mountain and caved in on itself, stopping the outflow. Scientists are now sure the lava at this site came from a very narrow slit filled with magma. From their earlier trip inside a magma chamber, the scientists now know an entire eruption can be fed through such a narrow slit. When the lava flow stopped because the passage was blocked, pressure mounted. 2 days later, the eruption shot up in a volcano crater, spewing out material that was chemically totally different from the lava that flowed to the surface earlier. Something happened to the magma on its way from the reservoir a few kilometers underground. A change that turned the magma from a peaceful lava flow to a furious and very violent ash cloud. But we still don't know the details of that process.
So, it's getting close to dinner time. The steel in the shovel is a good heat conductor, so it should work as a barbecue here. Extremely good.
With eruptions in Iceland happening on average every 5 years, the question is not if, but when and where. With some of the biggest and most active volcanoes covered by glaciers, the signs of impending eruptions will most certainly come from under the ice. Bursts of outflow from the Katla volcano indicate increased activity, also registered by the earthquake monitors. The normally crystal clear water is suddenly dirty and filled with particles, a telltale sign of increased melting and additional water flow. But is it an eruption? In October 2010, a large number of earthquakes and lots of ground tremor were recorded in the crater under the biggest of the glaciers. The Grimsvötn caldera suddenly woke up, and this is a very powerful place. The heat output from the geothermal sources equals the power production in a very large nuclear reactor. It's enough to melt a lot of ice in a very short time. The water flow increased dramatically. In a matter of hours, the water rose some 6 feet, quickly flooding huge areas. An observation crew was deployed to follow the events and give early warnings.
It started last week when we noticed unrest in the Grímsvötn area of the Vatnajökull glacier on our seismometers. Those were the first signs.
By taking water samples, they can quickly differentiate between the chemical fingerprints of geothermal water and that of a volcanic eruption.
The first signs of that would be earthquakes in the Grímsvötn area. There actually have been some earthquakes there lately, but nothing that indicates that there will be an eruption today or tomorrow. You never know.
After a few days, the water recedes and the tremors almost stop. This time there was no eruption of hot magma under the ice. It must have been geothermal activity, superheated water that boiled to the surface. But it's still a clear sign the volcano is awake and that processes are in progress. There is no doubt Iceland is moving into a longer period of increased volcanic activity. Even if the scientists understand the ramifications, they still look forward to eruptions.
I would like to see more eruptions, that's for sure. But I would prefer that they were not making all these problems and disruptions.
Yeah, of course I want to see the eruptions. These are, these are what we study daily, what's going on beneath the ground. Of course it's nice to watch the eruption as well. It's quite a display.
I would not be surprised if we have one in the coming months in Iceland.
It's amazing to watch. It is. Even though it has bad effects for people living there and so forth. It's nature's display.
Could a crater in Italy explain a Roman emperor's conversion to Christianity? Find out